So now, after the introduction of fluid mechanics, now we start with first branch of fluid mechanics. So that is fluid statics. So now we see what is the meaning of this term fluid statics and what are the various laws which govern the fluid which is at rest. Okay. So now this term fluid statics we defined as the study of fluid at rest. Okay. So this concept also includes the situations where fluids are either actually at rest or undergo uniform acceleration. Uniform acceleration in some container or rotate as a solid mass. Okay. So fluid statics means study of fluid at rest or the fluid which is moving with some uniform acceleration or fluid rotates as a solid mass with the container. So study of all such type of fluids comes under fluid statics. Now if we talk about a fluid element, now this fluid element experiences two types of forces. One we call as the body force. The second one are the surface forces. Now this body force that is caused by gravitational pull or by some electric field or by some magnetic field. So due to these, we have the body force. Now this body force is proportional to mass of the body. Okay. Now these surface forces, these are due to the surface stresses. Now the surface stresses are either due to pressure or due to shear. Now when we talk about the fluid at rest, then there is no relative motion between the fluid molecules. So there is no concept of shear. So the surface stresses are only due to pressure in case of fluid statics. So there is no shear. So there is no shear, that means there is no relative movement between the fluid particles. So that is the fluid at rest. So then the surface force is only due to pressure. So when we talk about fluid statics, any fluid experiences the force by pressure or by body force due to gravitation. If we neglect the other effect on the body force, that is electric or the magnetic effects. So the fluid which is under static condition experiences the forces by pressure or by the gravitational pull. Okay. So on the basis of this, we have certain laws for fluid statics. The first law we have the Pascal's law. So now to derive this law or to give the statement of this law, we consider a wedge-shaped fluid element. So that we have something like this. So this is a wedge-shaped element. This is direction X, this is direction Y, and this is direction Z. Now say this wedge-shaped element having dimension dx along x-axis. Similarly, this dimension is also dx, dy along y-axis, okay, and unity along z direction. Now this angle of this wedge is say theta, and this length of wedge is say ds. Okay. Now this wedge shaped element is made from some fluid and it experiences two forces when it is under static condition. One is the pressure force and second one the force due to gravity, that is the weight of this element. Okay. So now we find out the magnitude of those forces. So first there are two forces, we can write it as the first force due to pressure and the second force due to weight or gravitation, that is weight of the element. So now we find out these forces one by one. Now say this wedge shape element experiences the pressure intensity, experiences with pressure Px along x-axis, Py along y-axis, and P theta along the third wedge normal to the third direction, that is along the normal to the wedge. Now these pressures, these are acting along the normal directions. Okay, so along x-axis talk about Px, so that is along x direction and normal to this face. So this is Px, okay, and this is Py, and normal to third is P theta. Okay. So now we resolve these forces along x direction. Forces means we resolve these pressure intensities. So pressure intensities multiplied by the corresponding normal area, that give you the pressure force. And now we resolve the forces along x and y direction. So say first we write as the forces along x direction. So when we write these forces, so along this direction, you have px into area of the element is dy into 1. This is equal to the horizontal component of this pressure force. Now this horizontal component that becomes, now this is p theta. The normal force becomes p theta into the area. Area is 1 into ds. 1 into ds. So write it again. So this force is p theta into ds into 1. Okay. And if this angle is theta, so you have this angle also as theta. So this component becomes p theta into ds into sine theta. And vertical component is p theta ds into cos theta. So now you can write this px into dy into 1 along x-axis is equal to this component of force p theta into ds into sine theta. Okay. Now you can write it as px into dy upon ds into 1 equal to p theta into sine theta. Now this dy upon ds, so dy upon vertical upon this length, that is ds. So we can write this as sine theta. So our first equation is px is equal to p theta. Now you resolve forces along y-axis. So along y-axis we have the vertical force Py into area, this dx into 1 equal to this vertical component acting in the downward direction, p theta into ds into cos theta. So you can write it as py into dx upon ds equal to p theta into cos theta, or this dx upon ds, this becomes cos theta. So you have second relation as py equal to p theta, that is equal to py equal to p theta, that is equation number 2. So from equation number 1, no, there is one more force, sorry. If we talk about pressure, we have these two components. Now we left with the weight also. Okay. Now the part of that weight, so I rub this equation from here. Now weight of this element is also acting in the downward direction. Now weight we can write as, so here we have also write the weight. Okay. So we have py into dx equal to P theta into ds cos theta plus weight of this wedge shape element. Now what is the weight of this wedge shape element? Now weight we can write as, now weight you can write from the definition of specific weight. So weight is equal to volume into specific weight. So volume of this wedge shape is equal to 1 by 2 dx into dy into 1. Area multiplied by the depth multiplied by the specific weight from which the specific weight of fluid from which this element is made of, that is W. Okay, so this becomes 1 by 2 dx into dy into W. So now we replace this term weight by this one. So we write again Py into dx equal to P theta into ds cos theta plus 1 by 2 W dx into dy. Now dx into dy, these are very small terms. Now if this wedge shape element is similar to a point, then these dimensions dx and dy are very small. These are very small values. So the product of these very small values we can neglect. Okay, so now we left with Py into dx upon ds equal to P theta into cos theta. So this becomes cos theta. So these two terms cancel out and we left with Py equal to P theta, that is equation number 2. So from equation number 1 and equation number 2 you can write as Px equal to Py equal to P theta. Now how you state this equation now? Now this equation says that the pressure intensity along x-axis, so you can say at a point now. This equation states that at a point the pressure intensity along x direction is equal to the pressure intensity along y direction is equal to the pressure intensity along any other third direction which is at an angle theta. So now you can conclude that intensity of pressure at a point in a fluid at rest is same in all the directions. So that is our Pascal's law. This is the statement of Pascal's law. So the Pascal's law states that Px equal to Py equal to P theta. That means the intensity of pressure at a point in a fluid at rest is same in all the directions. So this is the first basic law of fluid mechanics. Fluid mechanics means fluid mechanics for fluid statics. So fluid at rest.